Yeah. So welcome to my presentation on how to read from streams and write things in Rust. My name is Ben Sparks. So just very quickly about me. Oh, alles gut. I did my bachelor's in Magdeburg and my master's in Heidelberg here. And since graduation, I've been working with Niklas at Aluga. Very first time I tried Rust is way back in 2015. This is before version 1.0. We're talking using tilde for boxes and the @ sign, I think it was, for some garbage collection way back when. But eventually I came back to 2020. And since starting at Aluga, I have been using it just about every work cycle we have professionally. So what this talk is going to be about, a quick refresher on what I.O. is, the differences between asynchronous and blocking I.O., as well as what streams and syncs are. And after we finish that, we'll discuss how reading and writing works in Tokio, or Tokio, depending on how you want to pronounce it, as well as how streams and syncs play a role in this. And at the end, we'll conclude with a practical demonstration of how to interpret protocols using codecs. So, I.O. Refers to reading and writing to resources. This is commonly files, but also very commonly network sockets. So Rust for reading and writing includes the read and write traits in the standard library, but these are blocking, which can be fine depending on your application. But the problem is that when you use them, you are blocking the thread they are running on. And this thread then cannot yield for another executor to take other work. So yeah, it becomes very difficult to do concurrent work. So in order to do concurrent work, we have asynchronous I.O., where we get to overlap the I.O. operation. So while some data is being read or sent somewhere over, be it onto the storage system, be it over TCP, your executor can do work with another thread while that job is running. And what are streams and syncs? So streams and syncs, streams emit potentially infinite data, while the syncs are capable of consuming this data. So when you use them together, you have a data pipeline that allows you to stream data that you can then optionally transform to whatever your task is, and you can process it in the sync without requiring all the values to be loaded into memory first, which is of course is prohibitive if you have infinite data because you don't have infinite RAM, right? So some examples of streams and syncs. So if you stream audio from a microphone, say at a concert, and this is being played over the speakers, we can't wait for the microphone to stop recording the signal before sending it through. So this is essentially a stream on the end of the microphone and a sync to whatever audio output you have. Also, if you go with something like sensor data, if in a weather station you have a thermometer somewhere measuring the outside temperature, you want to send this data in real time, you cannot stop reading the values from the stream, from the thermometer, before rendering it on the application. So you are essentially streaming all the temperatures that you are recording live into the application. And of course, very popular is TCP. You can asynchronously read whatever bytes come over the TCP connection from the incoming side before writing them back over the outgoing side back to the sender, which is again classic stream and sync procedure. So the question is, how can we do this in Tokio? Tokio gives us two big traits. These are async read and async write, and as the names imply, mirroring Rust standard I.O. traits, they allow you to read and write bytes asynchronously. There is also this helper method called split and various other derivatives dotted around specific types that allow you to split these objects that implement both these traits into separate objects that you can then use on separate handles, right? So TCP implements both, right? You read from the incoming connection, you write the outgoing connection, but you can split them into two separate halves if you want to process them in separate threads, right? Because otherwise you are borrowing the same object twice, mutably, and Rust borrow checker will tell you then This is not okay. Right, so you can move these halves into threads that are responsible for their tasks. And if all you want to do is simply read and write bytes, then you will get very far with these functions already. So within the I/O module, the copy function, I've abbreviated the traits here with R and W for async read and async write. If you want to implement a very simple echo server, this is all you need, right? You can simply pass in the read half for the async read, the async write, and Tokio will happily asynchronously echo the bytes back into the stream that they came from. A little more complex is the copy bidirectional function. This, in fact, would accept two objects that both implement reading and writing. This is perhaps a good use case for very simple proxy server, right? When the client connects to your proxy server, you can pass this to your A, and the outgoing connection where the client wanted to connect to is then your B. And then Tokio will happily asynchronously poll whatever bytes are written from either end back into the other end. And all this happens simply if you implement that trait. So you can drop anything in there without having to notably change your code, which is pretty cool. But usually you want, or not usually, you may want more from your byte streams. You may, in fact, want to interpret meaningful values from your byte streams. Usually, we like to call these frames. So if we compare, so we will produce essentially a stream of values from our byte streams. So yes, this does get quite type and trait heavy, and we're going to end up importing 3 different crates to make this work, but that's how the Rust ecosystem wants to be, unfortunately. Namely, we can look at the futures crate. So if we compare the async I/O traits to the future stream and sync, we start to notice some similarities. They both support an asynchronous production, but async read only produces bytes, whereas stream is a typed stream of values. And similarly, you also have the async write. It only works on bytes, but the sync will allow you to asynchronously write anything into it, well, as long as you fulfill the right type. So already you have this kind of mirrored relationship between the bytes and the values, so the only question that remains is how do we get from there to there? With another crate, it is part of the Tokio system. So a codec is an encoder and a decoder. The encoder is responsible for converting values to bytes, and the decoder does the opposite, bytes to values. And using these codecs, we can now essentially bridge the production of the bytes that we asynchronously read from TCP into the production of a stream of values. And of course, the other way out, if I want to write values to TCP, I can use this encoder. You also very handily have a result. So this is very useful in the fact that you have no guarantee what kind of bytes are being sent over your TCP stream. If someone connects to your TCP stream and sends any bytes they want, perhaps in an attempt to exploit your implementation, you can catch these malformed bytes and simply return the error that you want. The encoder also has this error field. I haven't really found a practical usage for it, except to signal that the message I want to generate is too long or I run out of memory, because it's very difficult to create errors from valid values when converting to bytes. But you can set this to whatever error type you want. This bridging, these are the last types, I promise, are implemented using framed read and framed write, also from the Tokio usual crate. They both take 2 arguments in the construction. One is the I/O source, so this one will take the read half, and this one will take the write half. You give this one the decoder, you give this one the encoder. When you have successfully constructed this, this framed read then starts to act like a stream of items. When you call next on this, it will poll the underlying bytes into the decoder and then produce them transparently as a stream. And similarly, when using framed write, it will take your value, it will pass it through the encoder, and then write it into your underlying data sync for you. And when you combine all these things, you start to realize that there are certain protocols that are very handily implemented by doing this. So the classic is to implement TCP-based protocols, at least for demonstration purposes. So the three things we have here are the asynchronous I/O from the Tokio trades. Depending on whatever your protocol is, your server may actually write to the client first, or your client may write to the server first. Right? So we have to handle these messages asynchronously. Decoders and encoders, they help us properly interpret the bytes that the client or the server may send, and of course transform them back so we can communicate simply in both directions. And the streams and sinks help us act upon these values so that we, as the implementers, don't run the risk of accidentally receiving or writing malformed data. Every time we actually want to interact with these data sources, we don't interact with them directly. We pass them through the decoder and the encoder, and if they are invalid, they will be rejected by the decoder and encoders respectively. Now, originally, I had prepared 2 examples. Who here is familiar with pixel flute? Yeah, at least, I see some hands here. Unfortunately, I can't do this one. I don't have my laptop. I wasn't capable of connecting to the screen recording software. But I do have an implementation of the NATS protocol with me. So that's quite cool. Implemented using the types shown before. So let's just concentrate on the NATS portion first. It's also the much cooler one, I think, personally. So NATS is a protocol whereby multiple clients can connect to a singular NATS server. And clients are capable of sending the pub message, which is part of the NATS protocol, to the NATS server. And any client that has subscribed to the correct subject will then receive whatever message was published from that client on the left side. There's also the matter of which client gets what, right? Because you see over here, we're publishing with the subject. This subject is an exact match for this one, therefore this client will receive it. This one does have a star here, but it will only match one level of the subject, and it can't match the Atlanta portion, so it won't get the message. And down here, this arrow here means match as many as we want, which means it will match the East and Atlanta parts, which means that the NATS server will then distribute the messages to here. But the great thing is that because we're just implementing the client portion of the protocol, all we have to do is ensure that the correct subscribers get the correct messages, and this handling of the messages is done by the NATS server itself. So to facilitate this communication, this is a very short overview of all the commands the NATS protocol supports. It's quite short, right? So at the very start, when a client connects to the server will immediately send this info command. And according to this info command, the client must respond back with a connect command that provides all the details, such as username, password, verbosity, pedantism. There's also some N keys authentication that's not specific. But after this connection has been established, clients can then start to publish messages, and they can start to subscribe and unsubscribe. And all of this must happen asynchronously. If you subscribe to a subject, then the server may send to you, depending on to which subject you subscribe to, this message at any given time. All of this is asynchronous. All of this must happen concurrently, and you must always be capable of capturing these messages. And you also, in fact, have to implement this ping-pong keep alive. But with the types and traits I've shown you today, it took me about, I'd say, 2, maybe 1.5 days to implement a working client for NATS that I can show to you. So this is the bare bones implementation. You supply a codec type, you simply call it this, and then you list all the commands that this codec supports. Right? These are purely the client commands, and you implement this trait for the codec, and you implement the encoder. Similarly, for the server message, you implement a separate set, and the advantage of this is that you can never confuse any of the bytes sent, because this decoder will only ever produce these client commands, and that decoder will only ever produce the server commands. Same goes for this. You cannot accidentally write a server command when you are the client, because the encoder here is strongly typed against the client command. So all of this makes it very easy to very calmly almost, and in a type-safe manner, send and receive messages to the NAT server. So I have with me this implementation. So as soon as I find the correct console, I can show some of it. All right, I'm going to have to get rid of. Yeah, jawohl. Okay, so take that, put that there. Maybe I heard a light theme might be appropriate, right? Is it a view? Nicholas, you wouldn't happen to know the button for changing the theme. Yes. Oh, that's right here. Must make a new profile. Yeah, there we go. Excellent. Right. So first, we'll give you the high view. Who here somewhat regularly reads the Rust subreddit? Somewhat regularly. Who here spotted the Sans.io blog post? Yeah. Yeah, there we go. Yeah, okay, so we can first take a look at the NATS codec. That's fine. This one I know. It's here. Right, and what we essentially do here is have an empty file. Just kidding. Yeah, so you simply, as before, where was it? Here we go.
Can you bump up the font size?
Increase font size, I hear. Yeah?
Thank you.
There we go. Yeah, so down here we have our server commands, strongly typed enum, and all the fields it can have. We also have all the client commands in here. And I'll show perhaps a brief overview. Yep, so these are all the errors that can be produced when a server message fails to decode. I simply made one per message that fails to decode. Same goes for the client. And yep, helper functions galore. Let's have a look. One of the client messages was, yeah, so the very simple ones is decoding a ping. They have an empty body, just a ping prefix, so they immediately succeed if you have matched the ping prefix prior. And essentially you have a buffer of bytes that you simply parse to completion. It's no different than writing a parse, but instead of parsing ASCII, you're parsing bytes. Yeah, no, this is probably a bit boring, frankly. Yeah, you know what? So, does tmux respect the theme? We had this before. Let's quickly fire that up. So basically all I did was parse the byte streams, make some messages. Oh, please tell me I've not forgotten the key combinations. I promise I had this. Do I need to look at it? Oh, I'm an idiot. I haven't started tmux. There we go. So I prepared two examples. You didn't see this one, that was never there. Right, I have a publisher, and all it does is write to the TCP stream messages that I pass through the encoder. This happens in an entirely safe manner. So there is a public instance of nuts that you can connect to, actually. So if we're going to mimic the example from earlier, I can start publishing this timestamp. It's probably a bit low, isn't it? Let's see if I can actually flip this quickly. There we go. Okay, that's good enough. Yep, so this is currently publishing that timestamp to the public nuts instance. If you want to and you have nuts client installed, you can actually subscribe to this and see it happen in real time. Do I have access to cargo? Nope, I don't. Cargo run example. I had this in my bash history on my actual laptop, so you have to give me a second. I can now subscribe to this. Right, and I give the same host, the same port. If I subscribe to the wrong subject, remember before it was time US East Atlanta, if I simply subscribe to time.us.east, I get nothing, right? Because I have not subscribed to the correct subject. If I subscribe specifically to @Atlanta, I can then start to receive the same messages. All of this happens using the same codecs. Both of these share the same underlying implementation. It's a very thin wrapper around that. I can even supply a max messages, as you have perhaps seen over here, so that this implementation will terminate simply after having received the time 5 times in a row. Okay, maybe that's a bit high, takes a bit long. 4, 5, right? Because again, that parameter is part of the NATS protocol. All I did was send it and then auto unsubscribe after 5 times. You'll also see there's this thing called a queue group. Well, if you could see it, it would be over here. NATS also supports a queue group, right? So in fact, I can simply say NixRust. And perhaps I can really quickly just steal this. That's not how that works. That's a shame. Right, I can subscriber. Oh boy, I regret making the CLI this long, I'll tell you that much. Hard coding saves lives, I tell you. What was it? time.us.east.atlanta. UE, that's not going to work, is it? There we go. So if I subscribe to the same queue group, then the NAT server will begin distributing these messages between the clients. So if I want this one to receive 5 messages, and I have the queue group 1, and I very quickly repeat the command. Sorry, that's meant to be NixRust. Yep, and I send this off at the same time. Let's have a look. We will start to see that these messages start to alternate between the clients. And again, that's nothing I've implemented myself. That's all part of the NATS protocol. The server itself chooses the correct one. But all because all I've done is implement decoders, encoders, all of a sudden I have the power to subscribe to any public or any running instance, as long as I provide the authentication details. Right? It's ping-pongs between. And all of that is contained in a very short NATS, I believe it is here, very short NATS.io. Is it SON.io or SAN.io? I'd never know. Opinions are welcome. That's not a call out. Right? All this is, no, that's not the right file. I am NATS codec. I implemented the client for it. Yep. Sorry, this was all open on my actual laptop, but it should be. Wait a minute. Wait a second. Yep, it is in there. Yep. You'll see up here the framed read and framed write. So this is a client, and it's a client in dark theme again. Right. So this is our client. It's connected to a TCP stream.
Can you bump up the font size?
Oh yeah, of course. My mistake. Right, we have a TCP stream here. We split it into its halves. And we create framed read and framed write with the codecs over here. And then as part of SAN.io, or SAN.io, however we're going to pronounce it, I can receive these. So this is pretty much, if you've read the blog post, an exact match of what appears in that blog post with an extended keep alive response, right? Otherwise, that example wouldn't run for more than 10 seconds. And all of this is just possible because we use type values as on our API boundaries using decoders and encoders. Yeah. So I know that was a long-winded one. I promise that is the end. Thanks for your attention. Any questions? Anything you want to ask? Go ahead. Yes, please?
So the decoder.
Yeah, decoding. Sure.
This time you can keep it because that was also.
All right. You want to see decoding?
So the decoder thing, you showed us the trait. It takes a bunch of bytes and then you get a result. Either you get a value of type T or your error if there is some kind of error.
Let's go for the client commands.
And my question is, sometimes you don't have enough bytes and the decoder sees that could be a valid message, but I would need more bytes for it. How is this communicated to the framed read?
Excellent question. So framed read knows nothing about this. It's purely inside the decoder. Namely, this is the trait implementation. And all I've done is, so NATS, you have to know about NATS's protocol structure, is that it prefixes every message with whatever kind of message it is, and then you can just start the corresponding decoder that you implement outside. But right as you are, in fact, there are NATS messages that are theoretically infinitely long, because there is the HPub. HPub supports headers, and you can theoretically supply as many headers as you want. So this is a real issue. What you do is, this over here, this return allows you to signal that. So if you return precisely OK none, this then signals to whatever does the decoding that there aren't enough bytes to produce a full frame. And then it will poll the TCP stream again, whatever underlying I/O source you have, put that back in the bytes, and then restart the decoding. Now, of course, this does present the danger that theoretically you can send a malformed message, and then it will buffer infinitely, and then our entire principle of streaming and syncs will be thrown out the window, because if we buffer everything into memory, then why are we even trying? So what every implementation must do is it must enforce a soft limit. In this case, I think the NATS documentation actually recommends setting it to 8 kilobytes. I think it has 8,192 bytes written down somewhere. I think I didn't see that until later. I put like 65,000 or something in there. But the point is, if the length of this source exceeds, I think I should have it down here. Yeah. If my input exceeds this buffer size limit, or doesn't exceed it, then you can ask for more bytes. But if it's too short, we can simply signal an error, and then it will reject the message, simply as too long, right? So I believe I have it down here. Yeah, I have exceed soft length and unknown command as separate enum errors that I can just pass back.
So the decode method actually returns a result option.
Yeah.
And otherwise an error.
Yes, so OK.
Because in the first signature, I thought I have read that it was a result T error. And then I asked myself how this could be done.
No, you're absolutely right. That does say result of t. It should say result of option of t. Or I can cheat and say t is option u, but yeah, absolutely right. Any other questions about reading bytes? Yes, please.
Maybe not about reading bytes in particular, but I also looked at the NUTS protocol in general. I thought it was very interesting. Do you have any experience in using NUTS for any particular project? And how was that? And
since the end of last year, working for this man in the front row, yes.
Yeah?
Yes. That's actually what led me to implementing this in the first place. I was very surprised to see it was such a simple protocol. What is the question about NUTS?
Sorry?
You had a question about NUTS?
Yeah, what the particular use case was where that kind of messaging applied. Or if it's internal, company internal, maybe then you can also skip that question.
I can go ahead, yeah? It's dangerous when the boss is watching you, I'll tell you that much. We have a worker process that can receive requests for jobs that may be restarted. So what we do is we send messages with payloads that contain the data required to start the job. And then this worker process will consume the message and start the job, or at least register a job in the queue. And then when enough processes are free, that is dequeued. If it fails, it is re-enqueued for the configured amount of retries. And finally, it is dismissed. And then that result is written to object storage somewhere, and you can recall it via the appropriate API. Okay. Right, so in our case, we have, so if we go back to that diagram.
But for the queue in particular, you do not use NUTS, because I mean, the queue use case is not really
no,
right?
NUTS does not hold the queue itself. It's an internal storage that simply creates a job queue that we then dequeue.
Okay.
Yeah. So it's the exact inverse of this diagram, right? We have one big worker process over here, and all the other clients in here are publishing messages into here, and this one is subscribed.
Okay.
But the great thing about NUTS is as long as you only implement that protocol, the majority of the logic is actually handled by that core server over here. So that's why I was able to cobble together this API for NUTS within a few days at most. Yeah, it's very comfortable to work with. Yeah.
A super short question from my side. Can we access your example that you just showed us? Because I also have a similar use case.
As of 10 minutes ago, it's public.
It's public?
Yeah, okay. So
in my case, I really have a similar problem, and I was not able to solve it. I mean, I only spent.
What kind of use case is this? Very briefly, possible?
Very briefly, we get data from it's like network flow traces, and we also want to queue them and work with them in order to, I don't know, apply some models to get some data behind.
Yeah, so essentially all you need for that, I mean, if it's just about starting jobs, then all you need
Not
is...
only about starting, but also re-queuing if they were not.
Yeah, well, once the worker process receives the measure, it can do whatever it wants with it, right? As long as it has the data it needs, then... Yeah, as long as NUTS passes it along, sure.
All right. Yeah.
All right. There's a question in the back there.
Maybe.
Yes, please.
It seems like the encoder and decoder.
Sorry, a little bit louder.
The encoder and decoder seem quite similar to SERDE. Is there some kind of interop that is possible, at least like for things like JSON lines or something?
So, in fact, I have seen a module that claims to, well, it provides decoders and encoders, but with JSON. So it does exactly that. It just calls Zer JSON from slice, I think, and then it just passes the bytes straight into there. But if it's JSON lines, then I haven't seen that, but that is very simply possible, because actually, as parts, it's spawned over here. Okay, I can quickly show this, because I know where it is, in fact. So let us go to, I believe, Tokio util. This is one of the traits, and it has the codec module, and within this codec module, it has a lines codec. So what this will do, when you pass it, here's actually an example. When you pass in your line delimited data as bytes, and you apply this framed read, you will then get that message separated by the bytes. So what you would do in that case, you'd say, you would create your framed read and do a while lets I receive messages, and then you'd pass that decoded message into Zerde.
Yep. Okay.
So, and the encoding would then just be, I think, Zerde two string. Not pretty, because that will add you new lines, but Zerde 2 string should be sufficient for that. Yeah.
Makes
Absolutely.
sense. Yeah.
All right. Any further questions? All right. Well, I hope you learned something new today and got to enjoy yourself with the practical demonstration. What's next? Break. Break time?
Then another round of applause.